Okay, obviously everyone can hear me. So on behalf of Haystack Observatory, I'd like to welcome you all to the 22nd annual Michael Buonsanto Memorial Lecture. I'll say more about our speaker in a moment. We have some people here in person, but I'm also glad to know that we have a much larger contingent out there online through Zoom. And we are recording this lecture, so those people who have colleagues who cannot make it can go back later and watch it either individually or with their group. So we've been doing this for 22 years, which is a hard thing to believe, but it's a testament to Michael's really enduring legacy in ionospheric physics. I always start out with a couple of things about Michael. What you see here on there we go. What you see here on the screen is Michael in his office on the left-hand side, which was the way that. Why did that happen? There we go. I don't know why that happened. That was him in his office, kind of smiling, getting ready to dig into a plot. And then on the right-hand side is what he would usually appear as conferences. The red sweater was how you could see him from across a 500-person room. So Michael was, in his regrettably brief life, he was a prolific publisher of articles. He had 70 refereed articles, 60 of them in the last decade of his life, between 89 and 99. 13 is the sole author and 25 as lead author. There were about 50 collaborators, which if you have good eyesight, you can see on the right-hand side there. 5 of them, I'm happy to say, were with undergraduate student co-authors through our summer student research program, which I always thought was very significant. And he spent more than 10 years in the summers as a summer student mentor in our Haystack programs. And various people came out of that, including Olivier Vatas, who's now a planetary science at European Space Agency. So Michael had an influence not only on publications, but also students. This landmark article on his review of ionospheric storms comes up all the time still. That's also an EOS article over there talking about, with Tim Fuller-Rowell, about strides made in understanding space weather and Earth. And this one, as you can see, the other article was accepted in March 1999, not that long after before his untimely passing. And I always do this every year. I pulled the statistics for this. In the last 3 years, he's picked up more than 300 citations of that paper, 22 years after he's been gone. So this is one of these papers that has a really long tail in our field. If you look at papers that get cited, there are certain papers that just continue to go. And so Michael's analysis in here, and I think, Jan, you're going to talk to a little bit of some of that today, is a real testament to why this article still continues to be foundational. Climatology, this is another subject he spent a lot of time on. You work with people here like John Holtz and Shenrong Zhang on the ISRAM climatological models and also on long-term trends. That was another part of his output. So just a brief remembering and a dedication once again of the lecture to Mike Buonsanto's work. So without further ado, I'm going to just introduce our speaker, and then I will turn the floor over to Professor Jan Sojka, who was our 2021 Buonsanto lecturer. So just a brief biography. Jan got his PhD from University College London and then spent a postdoc also there at the Mullard Space Science Laboratory. And then since 1978, he's been at Utah State University, where he is known to us for both ionospheric theory and also computational modeling of such. He's the professor of physics there and head of the physics department. And it wasn't in your bio, but I pulled it here. I found your citation for being the 2002 U.S. Professor of the Year from Carnegie Mellon Foundation. So I thought that was quite significant. More than 250 refereed scientific papers, co-editor of at least one heliophysics textbook, chair of more than one NASA science and technology definition teams, and a trustee for the NASA Space Grant Consortium, which is done by state. And so he's a trustee for the Space Grant Consortium in Utah. And so I'd like to turn it over to Jan. Thank you very much for coming to talk to us. We're really looking forward to hearing it. The subject from today is, would a present-day ionospheric servo model improve on Michael Buonsanto's 1986 ionospheric servo study? So Jan, I'd like to turn the floor over to you, and thank you once again for coming.
Thank you very much, Phil.
We're going to switch slides here just for a moment. Oh. Are you already doing that, Andrew?
I get to go. If you want to look it up, it's fine too.
We'll switch windows. Okay. There we go. How do we get that back on the screen here?
Presentation.
Yeah, just hit the usual.
Thank you. Well, it's my great pleasure to be here. I'm much honored. Personally, I kind of didn't really have a lot of interactions or anecdotal stories about Michael. I most certainly knew who he was and was at Cedar and other meetings when he was present. But to cut a long story short, what always impressed me, and that's what we'll talk about today, was the way he did his science. And that's kind of the emphasis of today's talk. Well, so it's a challenge really. Today, although we think we know lots more, do we do a better job of picking a particular challenging topic and then proceeding to use our knowledge, our observational data, our models to actually get closure to the questions we asked? And Michael was just excellent at that. So that's kind of where we'll start and hopefully end. So a rough outline. I hope to give you a little bit about the backstory up here before we get too far. Then we'll talk about his 1986 paper, and you'll see why I chose this one in a minute or two. The setup he has, the questions he asked, and then his findings. Okay, and then we'll introduce the servo more fully. And a servo has many kind of ideas depending which dictionary you're looking at. But I'll tell you the one you've got to believe, what Michael kind of proceeded on. Then we'll talk about TEC. If Michael's around today, he'd have his hands dirty with TEC. That's where we've got multiple observational databases that we can use to look at their ionosphere again. We'll talk about a quiet day study and then what happens during disturbed days. And then at the end, I'm going to give you the idea that in Michael's hands, this servo, which sounds engineering, was in actual fact, from his point of view, a forensic tool. You could actually set up questions and run these kind of studies to learn something about something you weren't measuring, which was kind of his objective. So let's proceed. So the backstory really is, to be honest with you all, I hadn't ever attended a single Michael Buonsanto memorial lecture, so I'm disappointed I never did. What I did look at was Alan Burns's paper from last year, and that kind of, if nothing else, also enthused me with regards to the Buonsanto 1986 paper. When you see in a second or two the connection, it'll make more sense. What I did find out when I was looking at this this question, has anyone published work on using TEC for ionospheric servo? I couldn't really find anybody who picked up servos. Servos kind of died out simply because the number of ionosondes available at any given time is relatively small. And to run a servo well, you need more continuous spatially distributed data. And of course, that's what TEC does for us. So that was the nature of my kind of question. That question brought me to Haystack. I came here in the summer, just this summer, with some ideas on using TEC. And where's a better place? There isn't really. Haystack, the Madrigal database here has a phenomenal TEC archive. Anthea and her team kind of put together. The property that I'm after is you don't smooth or introduce climatology into the data. You store it as original with all its noise and all its information kind of interpreted, if you like. So that was my reason for coming here. And to some extent, that's what got me here today. We're having our meeting, and Anthea and Phil disappear for a while, and they come back and arm twist me, put me on the table, and I said, okay, I'll do it. Okay. However, in all honor to our colleague, I would have preferred to do this as a view graph projector presentation today, but you didn't let me, so we'll proceed. This is what I'm referring to. Michael's it's 1986 publication, but the final date that the journal received it was 85. So the work was done 85 or earlier. And I'll mix the two dates together a little bit as we go. This was during a period of time where he had a 10-year sojourn in the Southern Hemisphere. He spent time, obviously, in Fiji as well. But last year, if you recall, Alan Burns talked about meeting him in New Zealand, where, of course, Alan Burns came from. So there was a link, if you like, to this paper and the time he'd spent in the Southern Hemisphere. So what was he doing? He was looking at seasonal variations, and it's the daytime ionization flows inferred from a comparison of calculated and observed NMF2. His ionosondes gave him a couple of parameters, the peak density, NMF2, and the peak height. And these two things he was going to use to mix observed with calculated modeled data. Now look at the date, it's 85. So if we fall back to then, the tools were slightly different, and we'll talk about that in a second. Okay, so Michael's paper set out to quantify neutral wind and topside fluxes. So at that time, we're talking about the mid-latitudes, and there is a good feeling that there's hemispheric flows and other things that we're familiar with today. But he was viewing these as the two major drivers of the mid-latitude ionosphere. And he was emphasizing the climatology. So a lot of us today talk about hourly variations, TIDs and storms. But Michael was looking at the kind of what we might call the climatology. So his focus, remember, is the peak density. This is the information that he believes is of good quality and can be used. And here's what he's after. He's going to try to get a solar cycle dependence. He's got data from 2 years, a minimum year and a maximum year. He's looking at the seasons, summer, winter equinox. And the summer and winter, of course, if you have both hemispheres flip over and are connected. And that was part of how he was going to extract information. And his ionosondes had a latitudinal distribution as well as, of course, local time. And he emphasized the noon sector, so we're not talking about nighttime. But the big thing he was going to manipulate positively was the two conjugate hemispheres. Okay, so what he had to work with were 10 ionosondes that provided F region density, the peak density, NMF2, and the peak height, HMF2. The equations of the ionospheric theory, MSIS, FORTRAN, and 1980s computers. So his hands are somewhat tied behind his back. The equations of the ionosphere, it turns out, they've stayed the test of time, and we still use the same ones. MSIS, of course, we also use today. Al Hedin's early versions were available, and he used them. And we all kind of love this text. How many of you still love FORTRAN? Yes, okay. And finally, the 1980s computers, we love them too. Okay, so what's he going to do? He has this first equation, and I'll give you a citation for this equation in a second. He is looking at this term, this equation, which tells you the time rate of change of the peak density. That's what he's after. And there's only 3 terms, and we'll talk about them in a second. So all he has to do to answer his question is to get these 3 things, okay? And what he's done is he's taken this equation, which comes from Rishbeth. So most certainly Rishbeth we're all familiar with too. And from an ionospheric theory perspective, Rishbeth's work and his colleagues way back in 7 to 8 actually labeled this equation a servo model equation. And that's where the word comes from that I'm using today. In this particular paper, Michael only referred to the servo through this equation. But in subsequent papers, and there's a whole family of papers, he worked extensively with other co-authors to develop the servo to its kind of full extent that was possible. So I'm still at this equation, and we'll just briefly give you an idea what he had to come up with. He had to figure out the production rate. So that's what's primarily sunlight created, and as far as his assumptions were concerned, you're on the day side, sunlight at mid-latitudes is the major source. Then you have to actually compensate for production with loss and diffusion. And again, there are more equations in his paper, but for our purposes, he had to figure out how to compute these terms in order for this equation to be solved. And then the piece that he was very innovative on implementing was the third term that you've got here is just F as in force. You have to worry about fluxes at the top. We're at mid-latitudes, fluxes connect interhemispherically. Then there's equatorward winds. If you blow equatorward, you raise the layer. If you blow poleward, you lower the layer, which influences the height of the peak and the rates. So all of this, Michael had to specify. And from that, you would then get the answers that he wanted. And it's not quite that simple, but we'll move forward. So the first term on the right-hand side was the production. Well, MSIS gives you the atmosphere in which production of ionization occurs. F10.7 was already available and indicated as a proxy anyway, the UV effectiveness of the sunlight. And from atmospheric explorer data hot off the press, there was enough information to give him the relationship between F10 and the various ionization rates. Then for our kind of recombination and diffusion, we needed MSIS again, a whole bunch of aeronomy parameters, relationships, cross sections for the recombination and diffusion. And then finally, the term that Michael worked on was the topside flux and vertical drift, how to work them in or where they even needed. So from that, you have to solve all of this and specify all of this at the peak height. And this is where I would call it the servo kind of concept comes in. His procedure was you have the data, and it turned out to be monthly averages in the dayside sector. The height, which you're getting from the ionosonde, immediately enabled you to work where is the neutral atmosphere, what's the various densities, and then fill in the three terms on the right-hand side, solve the equation, and generate computerized computer-generated peak density. And his job now is just to compare it. And that sounds simple. He does a comparison, and as you'll see, he wasn't happy because he had to make adjustments. And this is where the servo, if you like, in a simple way comes in. His first assumption was diffusive equilibrium, which everybody would agree isn't going to be right, but it's a good starting place. And you'll see why it wasn't quite right. But then you come into here and make changes on your assumptions. And this is what Michael was doing. The neat thing about the servo is it provides you new information about equator winds and or topside fluxes. But in general, it's parameters you have no way of measuring. Okay, so he's generating new knowledge based on physics theory, if you like, and data availability. Okay, so here's his ionosondes. 6 of them up here in Japan and the Asian sector, and then there's 4 in Australia. Ionosondes have good longevity. Most of you will recognize the names. These same ionosondes are still pretty much out there operating. So there are 40 years of good data plus still working. This is Suva in Fiji, and I don't know how much time he spent there, but this is his location relative to these ionosondes. And down here somewhere is New Zealand, but we won't go there either. But that's where Michael met Alan Burns. Okay, so here we go. NMF2, HMF2, 2 years of data, 76 was still the minimum. and 1980 for solar maximum. He computed monthly mean daytime values, 3 seasons, north-south hemispheres linked by the plasmasphere. So this was looking at this bigger picture, not just in one location. And physics model generated peak density, and now he's ready to play with these data. So here is one of only 2 or 3 plots I'm going to show from the paper, but it very quickly emphasizes what he was doing. Okay, this particular plot has the in a linear scale the peak density, NMF2, or the model density. There are 2 symbols being used. An open square represents NMF2 that's observed, that's the ionosondes, and then the calculate. In this case, this is from a diffusive equilibrium calculation, and this is the answer. The equation simplifies when you throw away the terms. On the southern hemisphere, the Australian sector, you get good agreement in equinox. This is the solar minimum equinox, as it turns out. The 2 sets of boxes, if you like, squares, match up, and they show the latitudinal distribution in the southern hemisphere. So he's got a really nice trend. In the northern hemisphere, which is your Japan sector, again, they look sort of similar, and he does point out that, hey, this data point he believes is actually accurate. He has no reason for discarding it, but it most certainly doesn't quite match up. But he just puts a circle around it mentally and moves on. Nowadays, we get similar things. But this is where you must have had the pleasure of actually doing analysis. These then represent the solstices. One solstice, and here's another solstice. What you notice in the summer southern hemisphere, it's summer here, it's winter in the north. And in the north, then, where the winter is, the open squares again, the open squares are for the observations, and the solid squares are for the model. There's a difference. And when you go 6 months later to the other solstice, the same thing happens. In the winter hemisphere, if you like, there isn't enough production. The model just isn't generating enough. Something's wrong. And of course, we nowadays would argue, well, if it's a wind, it better be blowing equatorwards to increase the density. And that's not so common on the day side. It's usually forward. So the flux might be the other solution. So Michael's then in a position now, given that under diffusive equilibrium conditions, the model and data do not agree, the stage was set to use the servo aspect to look for a more agreeable solution. So Michael's analysis, so he doesn't use the word servo at this time, but I refer to it as a prototype servo analysis, where he's using data, nudging his model, but the model has got lots of approximations and assumptions that he barely knows about, or we as a field of scientists are still working on learning about. So then the analysis provides quantitative results. So we'll see this in a second. So no, these 2 fields that he's talking about, the flux from above or out in, and the wind field, well, he calls it a wind field. In actual fact, what he's computing is a vertical drift, but he's relating that in latitudes, daytime, to a wind or an equator wind. And this is still true today. We still don't have easy ways of observing these parameters. Okay, so this is back to Michael's own work. This kind of plot threw me for a loop. How many of you think the JGRs are going to allow you to put your x-axis at the top of the graph? It was kind of, it took me a minute or 2 to get my bearings straight. I thought he'd done it, but no, he hadn't. So latitude again, in this direction, it's the northern hemisphere, in this direction, southern hemisphere. Now, what he's doing is looking at equator winds. So remember, there's no measurements of this. This is data deduced from this modeling effort that he's got going. So talk about the winds now. This is from a servo, U equatorwards in meters per second. So if it's a positive number, the wind is blowing equatorwards. And if it's negative, it's blowing polewards. There's three types of symbols on these plots, and they represent the different seasons, but the seasons as months of the year. So he's broken the year up into three. A circle is January, February, November, December. Triangle is March, April, September, October. And the squares are May, June, July, August. So if we start with the circles, so January, February, November, December means in the northern hemisphere, you're winter. So in winter in the northern hemisphere, he needed a very strong, wind poleward. But in the southern hemisphere, the circles are here. In the southern hemisphere, the circles are the other direction. So these are kind of negative, and these veer into the positive. And in the southern hemisphere, this is summer, and positive is suggesting you're blowing stuff up the field line. Then if we go to the other solstice, so 6 months later, May, June, July, August. Now the northern hemisphere is in summer, and in summer he's finding the same thing from his analysis. It wants to push plasma up the flux tube. And in the southern hemisphere, which is now winter, he points out that these large numbers may actually not be quite accurate. He feels that they do seem to be very large. And then finally, equinox, which is the triangles. They're pretty similar. So there's a general good feeling with this. And the other parameter he now gets is how much flux did he have to put into the system in order to make it balance. And this then becomes kind of more interesting too, because these are numbers that people kind of had inferred or tried to come up with, but weren't readily available, okay? The circles again are for the northern hemisphere winter. So the fluxes are quite strong downwards onto you. In the southern hemisphere, January, February, November, December is summer. And in summer, the fluxes are upwards and outwards. So I don't need to do much more on this plot, but we could do the other 6 months, May, June, July, August. That's deep summer in the northern hemisphere, the squares. Fluxes are coming up in summer and then down, of course, in winter. Okay, so that was really a real nice paper. I don't know how many of you have read it, but there's a lot more in it than just I've said, but I thought it was a really excellent piece of work. 1986 paper presentation complete. So we're going to move forward 36 years and look at what we might call a modern day servo. And then we'll have a look at today's research environment. So the really neat thing was in that paper, in the introduction, his very first sentence was, a vast amount of ionospheric data has been collected over the past 40 years. Now, that put in context of today left me stuck. So I struggled to find a more effective phrase than vast amount. Anybody who's looked at the databases we have, the word vast is totally applicable today. So anyway, that was Michael honored his predecessors too. So what Michael had was the ionosphere, and this is just a typical daytime example of an ionospheric profile at mid-latitudes. And this peak is what we've been referring to. It's between 200 and maybe 300-400, depending on various parameters. But the peak density is this number here, and the peak height is this. And this region is very easily influenced by the parameters, topside flux, the winds. Michael didn't refer to electric fields. He felt that he was working under moderate or quiet conditions. Okay, so that's what he had. And what we're going to do is spend some time now looking at TEC. TEC is the sum of all electrons between the transmitter, a GPS satellite, and the ground-based receiver. Now that doesn't mean it's vertically upwards. The ionosonde, you're looking straight above you, and in that sense, you had a simpler problem. Our problem really sucks, because as much as we use TEC in an everyday kind of, here it is, our ionosphere, it's not like that. The other plot, oops, 2 seconds. We only go up to 800. In fact, the bulk of the kind of ionosphere might be only up to 600 or something. It's a logarithmic scale, so it's dying away. But for TEC, it's not dying away. It's diminishing. Oh, and I apologize to everybody for this rather imperfect plasmasphere. 20,000 kilometers, 20,020, so just on the black line, is typically the altitude of the GPS constellation. But they're not above you, they're all over. And what we have is a slight problem. I want to talk about the ionosphere down here with our servo, but the plasmasphere starts about here all the way up. So that what you have is the total electron content is contaminated by about 5 or 20, up to 20%. So when we have a number that we call TEC and we look at an ionospheric problem, we're fooling ourselves. We're also looking at dynamics in this other region, which is quite independent often of what's going on down here. Okay, so ignore that and let's proceed. The ionosonde distribution used by Michael is going to be on this left panel, and we're going to give some examples of today's kind of distributions. We've seen this one before, and Michael thought that was vast, maybe vastly good. This is Japan, and we'll talk about this paper in a second. But every little black spot represents a GPS ground-based receiver listening to 20 or 15 or a large number of GPSs. So as you can see, there are many hundreds, if not 1,000 GPSs, and that's the kind of database we're used to working. The data set I'm going to show you comes from a database here at Millstone Hill, and for the particular study, I'm going to show you some data of these green spots represent the number that were used. The idea Scotland only had one is totally wrong, guys. This is, you know, no.
We have found the missing receivers. Just wanted you to know.
Okay. Anyway, given that, Julius Roux has a really nice ionosonde sitting somewhere down here underneath this large number of Swedish ionosondes, not ionosondes, GPS receivers. But otherwise, there is a really dense network, and as Anthea says, it's even denser than you're seeing. But we do have great kind of data sets. This one is maybe one of the first of the big papers that came out in 1998, showing that with just the GPS looking at TEC and looking at fluctuations of TEC at 10-minute intervals. So that what you have is, how many of you can see a seahorse that's got a coat? Okay, excellent. So we're on the same page. This seahorse, if you pick a point like its nose, and then go to the next one from A to B, oh, the red's moved. It's moved some more. Blue is coming back. The next piece of red, and yeah, it's not random color variations you're looking at. And this is this famous word TIDs all over the continent of, well, it's not this country of Japan. So this is just that data with almost no interpretation. There are structures referred to as TIDs. So that's kind of A, B, C, D. So that was very methodical. I show another plot, which is very common here. It's from the group here. Same thing happens. This is Northern Hemisphere, North America, and Europe. And what you're looking at again is A, B, C, D. So this time you don't go this way, you go this way. Okay, I don't know why you guys did that. But this one went this way. You read a book this way, but I don't know why they. So anyway, to cut a long story short, there's a structure. You'll look at the structure and then watch how it evolves and how new structures come up. And these are the structures that you might call Michael Mendelow's problems today. This would be the research world that he's in. It's ionospheric, it's mid-latitude, it's every bit as exciting. Things are happening that we don't fully appreciate or understand. So here's my acknowledgement to the team here. Sean Rong is the lead author, and all of you kind of appear here. And this was in 2019. And these papers really set the stage for what I was kind of doing this summer. What's a present day problem at mid latitudes? It's these traveling ionospheric disturbances. So what we have is lots of data, good quality data showing these things vary. Their amplitude isn't necessarily phenomenal. In our location at Julius Rue that I'm going to emphasize, the daytime noon is TEC, it's about 10 TEC units. And these fluctuations are only plus or minus 0.2. So it's not huge geomagnetic storms that we're looking at. And this would then be used today's ionospheric servo model to extract new information by tracking TEC through a physics-based ionospheric model. So let's proceed. Right away, I'm going to show you from the Madrigal, the MIT Haystack Observatory, Madrigal GPS TEC database at this one location. There are 4 days here. It's in July 2017, and the TEC, so that this is not the difference in TEC, this is just the measurement. And remember, TEC is measured not with one receiver looking straight up. It's an inference from many receivers potentially and many oblique paths. But anyway, what's really neat is there are no quiet days. Michael Mandillo, for years have been teaching us that there isn't such a thing as a quiet day. Or if you find one quiet day, there's never a second one. So the quiet day definition is poor. And you can see beautiful wiggles, and that's what we're about. Do they mean anything? So here, this is then, if I take my ionospheric model and just run it in climatology for this particular time, what do you get? And by and large, quiet time, we do reasonably well. That one day looks, really neat. I'll show that one again, right? Other ones, hey, these are multiple TEC unit errors. It's not 0.1 or 0.2. There are large differences. Okay, that's kind of where we are. So now I have to step into the kind of modeling world for a little while. In order for a servo to work, you have to have some parameter that you're observing, which when you see that thing change, it changes something else in the model. And that's what Michael was doing. When he didn't get the right answer, he could see from the physics of the errors or the differences, a vertical drift or a flux at the top would solve this. And in such a case, do the iteration again and again. So what I've got here is my model running for 2 days. And there are 9 different runs superimposed. So this is from nighttime to the noon sector, nighttime again. And at this time, just before noon, I turn on in each run the vertical drift. So the different vertical drifts, there are 9 of them. 0 is my baseline, if you like. And then I turn on all these up to 100 meters per second upwards, or minus 100 meter seconds downwards. And you can see that for 1 hour, I leave it turned on, and I want to know how it's responding, how the ionospheric TEC responds to that. So if I know there's a change in TEC, or a rate of change in TEC, I can infer how much for this one parameter. Now I've made an assumption, this is the parameter that's driving it. All the other parameters I've ignored, the fluxes and all of that, the composition. There are other things, but for our presentation, this is hot off it's never been published. It could be totally wrong, so don't reproduce it. Okay, so, okay. Of course, once it slowly then recovers over many hours, they do recover back to what you call the default quiet time. The really neat thing and made me feel really good was, hey, the response of TEC, the change in TEC to the magnitude and how long you leave the vertical drift on is extremely linear. These are the 8 different values I used, and it's linear going downwards as well as upwards, which I'm still not sure I believe properly. But that's the tool I then put into my system. And lo and behold, I run my servo, and most of you are looking at this and saying, well, there's only 2 traces, but they're not. There's 3 traces, right? There's the kind of servo trace on top of, if you like, the GPS. So this servo does exactly what you want it to do. It looks great. It's promising. So I'm moving forward. I'm pretending I'm Michael here. I mean, he'd be able to do this too. I've just picked one day of these. I've taken the one that's worst from the quiet day. So remember, the quiet day is the physics I'm putting in, except for the adjustment to the vertical drift. Okay, and there's my agreement. It looks like I've captured things. Now here's the shocker. No, yeah, there it is. Boom. Well, the same one day, here's the magnitude of vertical drift I'm needing. It's totally not right. Yeah, it seems noisy. It's more than 100 meters per second for a lot of the time. And it's going upwards and downwards, very high frequency. So my first thing to do is, what the heck am I tracking? It's obviously giving me the right answer, but what's going on? And this is where we come back to trying to understand our data and things. You say, well, maybe that's just a bad day. No, there's my 4 days. The tech agreement is pretty remarkable, but the vertical drift isn't remarkable. It sucks. In here, which is the best day, it seems to have the noisiest appearance. Okay, so what actually was going on was the following. I made a histogram of occurrence frequency, and all I'm doing is, as a time series, I'm comparing 2 techs, one tech and the next one, differencing them, and then making a histogram. Okay, and the GPS tech, this is the data that I'm using, gives me this distribution, and of course the TDIM, after you run this through the servo, gives me the same distribution, just almost perfectly. So it's mimicking information it's getting. And what it's mimicking is, if I were to assume they were normal distributions, 0.7 tech unit for GPS, TDIM is 0.5 tech units, the standard deviations are really large. So that data set, although it's a high quality data set, has not been smoothed. And that's the really important thing. I've not smoothed it, and it's got all the fluctuations. And let me just propose Anthea here and Phil and others that can see how close to the truth I might be getting. The resolution to this noisy problem is that it is not noise, nor an ionospheric phenomena. Rather, it is associated with the 5-minute, the analysis of the GPS slant tech paths and number of satellites are seen as changing. So there's a dynamic system. The satellites are moving, some drop out, and I'm almost sure that's kind of what I'm picking up. The TDIM-driven servo realistically is recovering this high frequency variability. The Madrigal Tech database has deliberately not been smoothed, and I don't really ever want to smooth it. I mean, the data there is authentic and real. Nestor Aponte, with Anthea's help, he generated for me a 1-minute cadence. Unfortunately, it got worse. So smoothing will impact the servo analysis of the TID. So that's not the immediate answer. So, okay, now you're asking, okay, it did really nicely during a quiet time. Most models can do that. Let's go to a disturbed time. Well, this is my favorite storm, 16th of July, 2017. KP was only 6. And it was a geomagnetic storm, but it was a nice one. So remember the quiet time curve for these 4 quiet days, followed by a storm day, and then 3 recovery days. And the recovery is a real nice one too, in the sense that because of the compositional changes, the ionization is kind of decreased significantly. It takes time for the atmosphere to rebuild. So it's a very classic kind of storm, and we would then go from that. Well, unfortunately, the model loves it. It follows every wiggle. That the relating the vertical drift to the change in TEC, the ionosphere is very capable. If that's the only thing you allow me to move, it just locks on without any trouble. What's wrong with this picture? Well, it doesn't. We know for sure during this time, the vertical drift isn't the only thing that's changing. The neutral atmosphere is changing. TADs, not just TIDs, are coming through there with large magnitude, perhaps even penetrating electric fields and other things. So in the micro Buonsanto sense, you stop here and go back into changing the assumptions and looking at other parameters. Even though you've got great agreement. One more. At night, using the neutral atmosphere of the quiet time most certainly isn't relevant. It needs to change. Okay, so much so. So that was the second problem in a big sense. The penetrating electric fields are ignored. Traveling atmospheric disturbances are ignored. They're coming from high latitude, sweeping down over us. Topside fluxes at the plasmasphere. During a storm, the entire plasmasphere has been wiped out and fluxes are going in different directions. And again, no effect being incorporated. Heating of the atmosphere and composition. There's a whole litany of things that need to be fixed. So it's non-trivial. During the recovery days, the neutral atmosphere is slowly returning to normal. Even just fixing that one thing would go a long way. Okay, so the word promising was there, but that's all it was. Okay, this is where Michael will apply a revision of the servo. So we'll move forward just into this. Michael had one more thing that we saw. In his study, he had a latitudinal distribution in both hemispheres. And the latitudinal distributions were very noticeable. And he actually did a really fine job of using that with the plasmasphere and understanding how the two hemispheres were connected. So what I want to do is look at the latitudinal variation. How can we use that? So this is its magnetic latitude in the European sector from about 35 to 65. What I'm going to show is a number of frames. I call it, it's not a movie, it's just a bunch of frames flicking by you very fast over between 6 and 20 local time. Noon would be here. So in this case, Europe is moving underneath us. We're always stuck at noon here. And what we're going to show is the storm time tech increase. So 0 is zero at the blue. So this is kind of like early on that storm day, 6 UT is when we start, and we'll go up to about 19 UT, and then it'll cycle. So it's not enough sophisticated simulate movie. Yeah. Negative is blue colors, and red is the kind of increasing TEC over the baseline. It goes up to 10 tech units, and the daytime noon value was 10. So it's almost doubling when this thing goes. Just to put it in context of what it looks like when it's kind of in the middle of the storm. We are kind of information again of the same latitude range. This is 1400 UT. You can see that there's now a rather, that the squares represent the binning I did. I did a 5-degree latitude by 1 hour local time binning, just to show the dynamics. It's the dynamics that Michael would have loved, I bet. Okay, so here we go. So we'll let it run for a while. Then it started in the north and then kind of came south. And now there's this very dense region around noon moving to the post-afternoon. And then it starts all over again. So although I haven't done any work with this yet, I only have that one site, the Julius route that I've looked at its kind of dynamics. The Madrigal database has this information in huge quantities. The dynamics is all there. And for this one storm, which is kind of a rather perfect storm, it would be a wonderful thing to work with. Okay, so I'm getting close to wrapping up. How does today's pursuit compare with those undertaken by Michael in 1986? So I'm cycling back for closure. What Michael did was he kind of set up his problem. The solar cycle, seasons, the conjugate hemispheres, we call that climatology, and that's kind of what he was all about. And he then used this idea of a servo, where he makes assumptions as best he understood them, looked at the results, compared them with data, and then proceeded to adjust things. And that kind of, I think, was really nice. Then today, well, I've identified one kind of topic that might be a kind of modern day Buonsanto kind of problem, and that was TIDs. We're certainly here at Millstone Hill with the phenomenal databases you've gathered, you're in the same position to do this kind of work. These include geomagnetic storm responses on hours to days, and the TID distributions on time scales of tens of minutes to hours. So again, we'd sure like to understand the drivers what that's driving the ionosphere into these things. Okay, so here we are, we're almost there. Today we are dependent on GNSS, GPS to know where we are. How many of you now drive with a Rand McNally Atlas? It's not a joke. It's a good question. You're putting Rand McNally out of business. You know, GPS has pretty much taken over, and we all depend on it. So this is a current hot topic, and Michael would just love to be in this. To get this correct, we need to know exactly how the mid-latitude ionosphere works. We live at mid-latitudes. We want GPS to not take us the wrong way, okay? Theory, modeling, and observations is what we're bringing together. And of course, I never talked about it until now. There's huge efforts doing what meteorologists do, which is just take this all together, mush it through an assimilation. And the trouble with an assimilation model is it costs you millions of dollars to create, and you can't go in and tweak. It's very hard to do that. You build it, and you build it with the best physics you have available, and then you run it. Most certainly, after 10 years, the second generation of these assimilation models are starting to look for how can we learn more than just give you back a three-dimensional ionosphere, but actually give you information about winds and electric fields and whatnot. So these things are pure production models, but there's basic physics that we need to do. And this is where this servo, it doesn't have to be quite the servo in my sense of the word I've shown you, but it's this forensic modeling where you can stop it, start again, manipulate, change, and then this leads us to one last little arrow. If we do this better, this will improve, I'm pretty sure, and of course our lights will be better because GPS is better, okay? So here's my kind of walk away. To answer the question, would a present day ionospheric servo model improve on Michael's 1986 ionospheric servo study? Taking a lead from meteorology, the more weather models you have predicting an outcome, the greater the spread of answers. And we're in the same thing. I mean, all our models are really good. We've tried really hard, but hence I think Michael did brilliant with the tools at his disposal. And we would do reasonably well. That's the end of presentation. Thank you very much.
Yeah, that was excellent. And it also is something that Michael would say often is the data are telling you something, and then the goal is to understand what. And I think that's exactly what you illustrated. So. Now, there's got to be some questions. I don't know if there are questions online. There might be. Is there anybody in the room that would like to ask one? I'll pass the microphone to you. So, while Andrew checks.
There is one question from Leaf Svalgard. How does this work for the E region?
Okay, so the question was, how does this work for the E region?
Okay, the E region is important for perhaps other reasons and not necessarily GPS. So the F region that I love kind of sits on top of the E region. Most certainly, there are many unknowns in the E region. Take the polar, perhaps the polar auroral ionosphere. The E region is still open to getting all these inputs correct. I would suspect dedicated E region physicists working with much more limited data than we have. Although GPS E region data is kind of just over the horizon, I think you could build servos very effectively for the E region and address outstanding questions. Thank you.
So Frank Lind in the room has a question.
So one of the things I wanted to ask is, I mean, you're taking this and taking a variational approach to kind of your model analysis. And, you know, underneath it, there may be an ensemble of parameters that are actually varying really in the atmosphere. And so you're picking out one and freezing the others and seeing what the effect is. And I was wondering what, you know, there's other things that I think go into this, such as the filter functions or transfer functions that are involved. And so even if you look at it from like a control theory feedback point of view, you would normally naturally apply filters on things. So when I see your model tracking very, you know, very tightly and then producing winds that are kind of, you know, spectacularly out there, I immediately am kind of wondering, well, how do we know that the transfer function that it's going through is anything close to correct? Because there really ought to be a filter on that. Similarly, there may be lagging going on. So you really would need to take this and explore it as a function of lag in order to see if there's optimal time delays for various, you know, phenomena to be influenced. So I don't know if you've looked at that and yet. And
The lag I have looked at, it's beautiful. It's exactly what you'd expect. 5 minutes. You know, you push it 5 minutes and then it does exactly that. So yeah, I agree with you entirely. I would not claim, and I'm not going to publish this as the vertical wind. Okay, you're seeing stuff that's kind of in the development experimental stage of modeling, and everything you said, Frank, is correct. That I just figured for Michael, I was prepared to show you dirty laundry. You know,
fair enough. Great, thank you.
Any other questions? Oh, Sharon has a question in the room.
Thanks, Jan. That's a very exciting talk. And we know this self-model developed a long time ago. At that time, the computer was not advanced at all. So that was probably the main reason why Henry Rishbeth developed that theory. But that theory is not, it's not anything special because it started from the continuity equation and integrate as function of height and get a simplified form. But that's a very simplified form, I would say. So now you have this advanced theoretical model of TDIM. I think you would do much better than just using the old-fashioned old model. And the indication that you show the winds has large fluctuations. I think it probably means that while this theory probably is too simplified and lack of variation, it's probably not due to winds. It's due to something else that contribute to the changing in the ionosphere. So
no, you're completely correct, Sharon. The understanding of kind of the data I showed you, the runs I showed, is more complicated than attributing it to winds. It's just that the one test I ran, the one assumption I was studying, used the change in tech relate 100% linearly to the wind, the vertical drift magnitude. And that, I agree with you, is a starting place. And it's a starting place that we close the door on very quickly. It's only, it's important, but it's not important in the order I showed. Plus, I do believe we can sit down around the table and figure out why from one 5-minute step to the next, the TEC varies this much compared to what you might call just the TID modulation amplitude of 0.2. That would clean this up, I think, enormously.
so some of the probably just some of these alloys not probably geophysical.
Anthony,
Well, so I was wondering if it would be worth looking at perhaps another location where we might not see quite as much variation.
Mhm.
And perhaps tightening up I don't know what elevation, when Nestor ran the second set for you, I would probably make it
So,
higher elevation, tighten it up. Because you're right, I think that the fluctuations are large, but remember, it's measuring all the way out to 20,000. So what we don't really know what's happening that high up.
So the really neat thing that came out of the TDIM that I didn't mention was that the TDIM only goes up to 800 kilometers. And of course, when you then say, well, I'm going to try to compare that with the TEC from GPS. Well, 20% or 5 to 20% of that TEC doesn't belong in the ionosphere I'm talking about. And the model run told me I had to remove 18.5%. So that just do that simple first step. I did do that. So I know how much plasmosphere I was kind of throwing away.
Larissa, and we should keep track of if there's any other things on the list. Okay.
I'm thinking of very interesting presentation, and very interesting details about how work that Michael did so many years ago is really relevant to open questions that we're facing today. One aspect that I wanted to mention, and I think like adds additional complexity to all the processes and mechanisms that we're discussing. You mentioned several times that vertical drift that you consider results from variations in the thermospheric meridional wind, but a lot of results that like over the years indicate also importance of zonal winds. As thermospheric zonal winds, in particular, a variation in thermospheric zonal wind and declination angle. And that would create like very different types of variations. Just changes in the zonal wind system would create different types of variations over in the ionosphere over different regions, depending on the declination angle. And that adds another level of complexity and another level of another interesting aspects of science that would lead to strongly regional variations. And I think we had our group had a number of papers about this led by Shanron a few years ago, I think 2012, right?
Something like that.
Yeah. Yes, and we are continuing this work with like some other approaches. But so this is additional aspect that Michael of course could not consider because he looked at one longitude, and you looked with your data. You looked only over Europe, right?
Just
yeah. But if you start looking over different regions, you will be able to see additional contributions from
declination. Yes, no, you're completely correct, Larissa. Yeah, we don't in the TDIM. We can do an offset dipole, but it's still a dipole, so that the TDIM is going to be limited for that kind of study. It needs next generation beyond that. But it's going to be what you said. For example, over the southern hemisphere, Madagascar, the declination problem down there, any of our physics models is pretty bad. Get the declination right. So yeah, you're completely correct.
Well, you got one on one? Yeah.
It was just a comment. So David Thomas was saying, yes, it is very likely that a lot of that variability is projection and other data challenges. For example, let's see, he's coming live actually.
Oh, sorry. I was just saying that, yeah, the jumps that you're seeing in tech are very, if you're using the binned products, then it's very likely that those are just rays entering and leaving the pixel. You'll get a lot of variability just as a result of that, because if a ray is coming, or if an IPP is moving into the pixel and it's not exactly at the mean of the population in the pixel, then it's going to cause a jump. And each of those rays with their different orientations through the pixel are going to have different orientation biases, associated with horizontal gradients in the ionosphere. So, and Thea's suggestion to limit the elevation is a good one, but you're probably still going to get a little bit of, probably unsavory variability just as a result of this concept of binning.
So I agree entirely. So the servo did find something. It confirmed that the data nature, the nature of the data, its variabilities. Thank you.
Yeah, just to follow up real quickly at that, the bin data, the real focus there is the absolute TEC. And all of those have a receiver bias associated with them, which is relatively large, that error. So as you're right, as a new satellite comes in, all of a sudden you have a different error coming in. And which is why when you look at the line of sight TECs, things are so smooth, because in that case, it's just a constant receiver bias and it's just disappears from point to point. But my other question was what a question that Phil would like me to ask. So if we did this kind of thing under a nice ISR that ran all the time, how much did you go pay me for this one, Chris? But then couldn't you constrain your model by having some of those physical things measured all the time? And we're talking about a meteor wind structure under here too. So that seems to be like a nice thing if you had nice instrumentation underneath the TEC data to constrain the circle model.
So my only real, as a modeler, I need the data from everywhere all the time. But the DAISY
We're all in favor of it.
The DAISY world that we're kind of seeing develop, as a step in a good direction. But the work I'm showing, please don't take it as publishable work. It's work that's just exploratory. I mean, I asked the question, has anybody attempted to do a servo using TEC? And I think the answers are, we should be able to get around these little hurdles that we're talking about. What we're after is learning something new. And it's just at the beginning, I hope, rather than the end. I walk away here quite enthused that Michael would be enthused. And that's good.
Any other questions either in the room? I don't know if there's anything else on there.
David just had a follow-up comment as well.
David, if you want to unmute, you can.
Sorry, I can't keep myself from talking today, I guess. No, I was just going to say, like, even if your biases and phase leveling were perfect, you'd still have issues because of the convolution of horizontal variability or horizontal gradients into this vertical tech estimate.
Yeah.
So, regardless of instrumental errors, there's this kind of fundamental problem if you have a measurement that's not vertical and you're trying to treat it as vertical. And there's always going to be problems because of that. But if you have a very dense network like they have over Europe, then you can kind of get past some of that problem by just restricting the elevation.
So the other thing that I didn't mention, during the storm, the TDIM can pick a trajectory or one flux tube and follow it. During a storm, that flux tube, even at mid-latitude, doesn't lie over Millstone Hill ad infinitum.
Right.
It moves according to the penetrating electric fields, and so that the actual study does need two-dimensionally extensive data if you're actually going to realistically follow during a storm time one of these. Even at this point, clearly, I don't know the processes hooked up in a way that would be appropriate.
Another comment and another thought. So I kept thinking when looking at these results, trying to look at different temporal scales, actually going away from short-term variations in TEC, but looking at climatological picture, either in TEC or peak electron density, and using empirical models for that. We have a large set of empirical models. So we have several empirical models for interference arena, but we also have developed and kind of in process working on empirical models of ionosones and total content with a really pretty large, so that carefully describe solar flux and seasonal variation. And seasonal variations could be really quite different in different locations. And like in a climatological sense, I think if we combine that type of data with simulations that we do, I think we really can expect a really realistic wind system from your model.
Yeah, I do believe you're right. I haven't gone there, I haven't started down that path, but you're right, that the databases, the empirical ones, do represent some information truth. And whether it comes out as the mean winds or the mean, it's not obvious necessarily, but most certainly it would say something very constructive. And I would do the declination right.
Yeah. Any other comments? Okay, in that case, before we thank our speaker again, I do have something to present to you. Now, let's see, I don't have 3 hands, so I'm going to drop this for one.
Microphone for you?
Yeah, I will hold the microphone. Oh, right. This is like Christmas, you have to unwrap.
No, I get to unwrap it.
So we present people with a plaque. This says Michael White J. Buonsanto Memorial Lecture Series, presented in grateful recognition of the 22nd annual lecture given by Jan Sojka, CAS, Department of Physics, Utah State, November 22nd. So Jan, we hope this is some remembrance of you giving us an excellent talk. So thanks once again. I've learned a great deal and I thought it was inspiring. So thanks once more. And so those of you in the room and those of you online, good day or evening or middle of the night, wherever you are in local time. And this concludes the 22nd annual Michael Buonsanto Memorial Lecture. The lecture will be posted on the series page for those of you who wanted to provide it to one of your colleagues. And thanks again for joining us.
Thank you, Phil.
That was excellent. That was really excellent. And you know, great thing about filtering.
I just realized